Hello everyone. My name is Ming, and today I'm going to share our work's visual-based parameterized proximal policy optimization. This is a joint work from Mehrjou, Huang, Zhengwei, Yang Shui, Linhai, Wei, and Peishu Huang. Most reinforcement algorithms only have a better performance in converge to the grade policy in a specific action spaces, but it's hard for them to optimize under the hybrid action spaces. So to address these problems, we propose a new algorithm called the parameterized proximal policy optimization (P3O), and we verify that under three environments: the robot curve soccer simulators, robot arm grasping, and pushing, and the results show that the P3O have a better policy in the end and higher convergence speeds. So if you are interested, please come by our poster and to watch the demo video and know more details. Thank you.
Hi everyone. This work is about filtering in dynamical system. Filtering refers to estimating the true state of the dynamical system given the measurements. It's about filtering, and this is about like estimating the true states of a dynamical system given the measurements. So normally in dynamical system, or like the Gaussian filtering, which is used more often, is the limitation is that the posterior is Gaussian, and also the mean of this Gaussian is a affine function of the measurement. So we tried to lift these two limitations by using the architecture shown in the section 5, and also using like optimizing the loss function shown in section 4 by end-to-end training. So yeah, for more details, please come stop by my poster. Thank you.
The state aggregation is a very useful tool for dimension reduction in complicated systems. We take the soft state aggregation framework for a large Markov transition process. So the state transition is viewed as first transiting to one of the few latent matter states using the aggregation distribution, and then transiting to the raw states using the disaggregation distribution. For complicated black box systems, these matter states and the disaggregation distributions are unknown. And our paper provides a method that directly estimates them using the state transition data. Okay, so we basically first introduce an anchor state notion to ensure the identifiability of these distributions. Then our method takes the singular vectors of the empirical transition probability matrix and then use a few closed form operations to convert them to the targeting distribution vectors. So it's computationally very fast. And you are welcome to our poster.
Hi guys, I'm Sharad and I'm here to talk about Solar. So the aim of Solar, it's a model-based reinforcement algorithm. Model-based reinforcement learning algorithm. The main objective of model-based reinforcement learning algorithms is hopefully to be more sample efficient than other RL algorithms. And we've seen great success in these algorithms in, for example, learning robot policies from states. But model-based reinforcement learning, it can be tricky to train a model directly from images. So the goal of our paper is to basically use representation learning to convert high-dimensional observation spaces into a low compact one, such that kind of traditional old-school model-based model-based control methods will work. Our approach is basically to first collect a bunch of data using a random policy. We then fit a variational autoencoder with a Bayesian linear dynamical system prior, and the hope is that this prior really helps out kind of old-school control methods work better. We then kind of go into the traditional RL loop where we fit some sort of local dynamics model and then iteratively update our policy until we've converged to our desired, until we've solved our task. We have a real-life robot example where we train this Lego stacking Sawyer bot to stack from directly images, no access to state information, in only 25 minutes, approximately on the order of 100 to 200 collected episodes. Please check out our poster if you want to learn more about the details of this method. Thank you.
For our method, the high-level overview is we just collect random rope movements in order to collect the data. And then from this data, we use a causal infogain model, which is a generative model that learns like a causal latent representation. So once we embed our start and goal states, we can create a visual plan. And this allows for a very interpretable method. And then after we have our visual plan, we learn an inverse model that can actually execute and follow this visual plan in order to follow through and execute this visual plan in a way that we can understand.
Hi everyone. So our work is on learning procedural abstractions with MR Brunskill. So the idea is you have many demonstrations on YouTube or other places. You can collect demonstration data very easily. And what we would like to do is to collect this data for procedural tasks where the demonstrator is trying to execute a sequence of steps. And we can then leverage these demonstrations to do a learning from demonstration. So for example, here we have sort of a cooking video and we maybe want to teach a robot or a human to do this. And so in this work, what we do is we describe how you can leverage shared structure across demonstrations to learn the latent procedure that the demonstrator is trying to execute. So here, for example, you have this cooking video for making meringue, so you can try to discover the sequence of steps that the demonstrator was trying to execute, sort of like a policy sketch of the demonstrator directly from the raw observations, and we describe a model to do that. And in the future, what we want to do is use this model to do control. Thanks.
So we're very interested in principled approaches to policy composition. So that is, if we know how to solve the task defined by the reward functions 1 and 2, we want to zero-shot solve tasks like RB, some combination. And we use the maximum entropy RL objective, which arises naturally from an RL as inference view. And it's important for composition because it prefers multimodal solutions. And so to solve composition under this objective, we extended two important ideas from discrete deterministic policies to maximum entropy RL and continuous action spaces. So successive features are an idea about how to decompose value functions so that you can revalue them on an additional task. And we use this value information with generalized policy improvement, which says that if we know the value of a set of policies on a task, we can act according to the maximum action value under any of those policies, and we're guaranteed that when we do this, we get returns at least as good as any of the existing policies. So in this work, we prove an extension of generalized policy improvement to the maximum entropy RL objective, and we introduced a practical algorithm for using adaptive importance sampling for solving these problems in continuous action spaces. And we solved tasks on things like the ant. And what's notable here is that despite the composition taking place per time step in the action value, we see structured trajectories arising. Thank you.
Hi, I'm Zhengwei. I'm here to share our work on inverse POM-DP. So in most of our neuroscience studies, it's the brain activities related to measurable things. I can see what you see, I can see what you do, but I cannot see what you think. So in our work, we use ideas from reinforcement learning to model an agent's behavior under an uncertain environment. We find a generic way to model their behavior and to infer their beliefs. So in other words, to read its mind. We assume that the behaviors of animals is optimally according to a partially observable Markov decision process, but with possibly incorrect model of their task. So based only on measurable things, its actions and sensory data, we find the model parameters, reward functions, and time-dependent latent beliefs that have the maximum likelihood. So we have applied our method to a rich class of foraging tasks widely used in neuroscience. where animals search for food with both ambiguous sensory cues and their memory of past rewards. So for simulated agents, we are able to recover the true model, and now we are ready to apply this to real data. So our work laid a critical foundation to understanding how the brain represents and computes with dynamic latent beliefs. Please come to my poster to find out more details. Thank you.
Hello, everyone. I would like to share my recent work with Zhang, Changyu, and Lawrence. And this work is done with an internship with Adobe. And the main motivation of the Thompson sampling by optimal transport is that the Thompson sampling is a widely used exploration strategy. And vanilla Thompson sampling has intractable posterior in many practical problems with nonlinear models such as neural network. So the main motivation of this work is that we develop a scalable Thompson sampling based on the Wasserstein gradient flows. And we name this method as particle interactive Thompson sampling, or PITS. And since Wasserstein gradient flow is a principal approach to approximate the posterior, and the PITS is based on the discretize the Wasserstein gradient flows to update the posterior. Intuitively, we will update the posterior while update the particles. And this figure illustrates the Wasserstein gradient flows. And the black balls are the elements of the probability measure space. And it also represents the posterior distribution. And the evolution of the posterior distribution is constitute the gradient flow. And And our experiments on the real-world experiments shows the significant performance improvement over the baselines. Welcome to our poster to learn more details of our work. Thank you.
Hi everyone, I'm Linhai here from Oxford. So actually in most robotics tasks, we know that we do have some existing approaches or heuristic controllers that can solve the problem in some degree, but not perfectly. So in our paper, we are trying to integrate this kind of heuristic controllers into the learning procedure of an off-policy deep reinforcement learning approach like DDPG. And what actually we did is that we introduced a stochastic switch which can select the actions proposed from either the DDPG or the heuristic controllers. Like we can see here, here is the DDPG, and here are some other independent controllers. And our switching network can learn a strategy to sample the actions from all of these, actions proposed by these three controllers. And during our experiments, we found that with this mechanism, the DDPG can firstly learn from these heuristic controllers as its policy is really bad at the beginning. And at the late stage, when the policy of the DDPG becomes quite good, it can learn to drop all of these heuristic controllers. And in this time, we can turn off the switching mechanism, and the DDPG can continue to learn by its own exploration. And for more details, we can discuss in the poster session. Thank you.
Okay, let's thank all the speakers. Very exciting works.